And for showing you how you can do better, we need to work out what the combinatorial structure of this range-min query problem is. And it turns out that there's a lovely, even bijective structure that corresponds to this problem. For that, let me first draw, this is just an array where the numbers are drawn as poles. The higher the thing, the bigger the number. And then you can visually think about range-min queries as picking a certain range in the horizontal direction. And then let a line fall down from plus infinity until it hits one of the poles. Now, to make the pictures nicer, here I'm using max queries instead of min, just because it is nicer to draw poles of positive height. Of course, you can always flip all the comparisons around and make max into min or min into max. As long as you need just one of the two, it doesn't matter which one you solve, you can always negate and get the other. But here, just to make the pictures nicer, everything's a range max now. Okay. Then again, so the picture is you take this bar and let it fall down until it hits the first pole, and that's your maximum, obviously. And the position where it hits that is the range max. Same definition, just explained visually. Now, how does that get a combinatorial structure? We could build a tree by taking the entire range over the entire array. So initially, I'm going to kill this pen eventually. Still works. So you let a line covering the entire array sink down until it hits the first pole. And imagine it's a brutal pole. It just cuts the line in half. And so now the two left and right parts can sink individually down, independently of each other. So this one will indeed sink all the way down to this pole, whereas the other one will stop earlier. Okay? Whenever they hit a pole, they become split and independently keep falling down. Also, whenever I do this, I have a single first hit pole on the left and one on the right. Again, type breaking, take the leftmost if there's several. And these we connect to the previous whole array maximum with child links. So that's going to be the root of a binary tree with these two children. And I can recurse in that this line here, it used to be, from here to here. Now these are two independent lines that again sink down between these two tall poles. And so they keep going, and I get more and more nodes until this is the final picture. Okay? The way to get the tree is top down, is the direction, and then you recurse on left and right whenever you have a maximum. That's a cute tree. What does that have to do with range maxima, though? If you look at a range like our red range here, there's going to be a leftmost and rightmost node, maybe in red, in the range. That's going to be these two. Now, the range maximum is the lowest common ancestor of those two nodes in the tree. If you walk from those up to the root, at the very least at the root, they have to join paths. And they usually join a bit earlier, in this case here. And that node, this is again, the way I draw the trees here, the root has to be between those two. One way to see that is I've put the indices in the nodes here from left to right. These are the indices of the array. Then the tree we built happens to be binary search tree ordered. All the numbers on the left of a node are smaller than all the numbers, or smaller than the number in the node and smaller than all the numbers to the right. As in a binary search tree, it's obviously by construction because we just split in the middle. So you could also say these numbers in here are exactly the array indices or the in-order index in the tree. If you do an in-order traversal of this binary tree, whenever you see, when you visit a node, you mark it and increment the counter, then you get the same numbers. Okay, then the lowest common ancestor where the paths to these two nodes split for the first time has to be between those, because that's a point in the binary search tree. Think about it. It was a point where we decided that 6 is smaller than 9, but 14 is bigger. As long as they're on the same side, the paths don't branch out. Okay, maybe that's helping to visualize this a bit. So we've reduced the problem of range max queries to finding lowest common ancestors in binary trees. That may be useful or not. The way how we will use it, the way why it's useful for us, is primarily that since this is all about the tree, we don't need to know the heights of these poles anymore. All that counts is the topology of the tree. How many, what nodes are there? What are left and right children? We don't need the information of the numbers. And that's useful because there's fewer ways to build trees than to arrange numbers. Here's a Slido question where your task was to find where the minimum in this range lies. And there's going to be an array that tells you by numbers, but we can figure this out from the tree. Since we're such a small group, maybe we don't need the Slido question. And you can just quickly work it out. Volunteers. And remember, we start counting at 0. First, we need the in-order traversal of the tree to mark the nodes with their index, with these numbers, because otherwise I don't know what 1 and 5 means. In-order traversal starts at the root, then goes left as long as it can, and when that's no longer possible, when you return, then you visit the current node. Then you go recursively right. So I'm going left, 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 then I can no longer go left, so I come back, and this guy is the first one I visit, so that gets 0, right? Then I'm done with this subtree because right is empty, so I go back up. Now I'm done with left for this guy. Now I visit this node, gets the 1. Now I'm going right. And then again, I'm trying to go left as long as I can, but there's nothing. So I come back and then I'm at this node. I visit it, so it gets the next number. And so on and so forth, okay? The way I drew the trees, you could also say it's a sweep line from left to right. Whenever you hit the nodes, they get the next number. But this is because I drew them in the sensible way you should draw binary search trees. Okay, so we can identify the two nodes we're talking about, 1 and 5. In this chapter, I made the endpoints inclusive for no good reason other than lack of interest to change the pictures. So where's the range max? What do we have to do for these two? We have to find the lowest common ancestor, which of course you can do by walking up and seeing where the paths meet. So that's the guy at index 3. Okay, good. Here's one way how this array could look like that gives the same range max position. There we go. Now, how is this useful for our data structure? As I said before, we don't care about the actual values, just the tree counts. So let's count the trees and see how many different ways range max queries can look like. The good thing here is I didn't stress this carefully enough. Is really a bijection. If all you know about your array are the range max answers for all possible ranges, you can still reconstruct the Cartesian tree. And if you have the Cartesian tree, you can still reconstruct all the range maxes by definition because they're given in the tree by the lowest common ancestors. So the two are exactly equivalent. knowing all answers of range max queries or knowing the Cartesian tree of an array. That also means I can count binary trees to count how many different options I have to answer range max queries. For example, here is my small tree, and it has, was it eight nodes? There's only a certain number of different trees with 8 nodes that could be a Cartesian tree. And the precise answer are the Catalan numbers. If you have n nodes and you want to build a binary tree, then that's the precise answer how many you get. For example, if you said n to 3, then there's 5 options. There's this tree, there's a lopsided one, the symmetric one, and the balanced one. And hopefully if you insert 3, this works out. So it's 1 over 4, and then 6 choose 3, otherwise known as 6 factorial over 3 factorial, and the 4. So you have the 6 factorial, 6 times 5 times 4. There's only the 6 times 5 left. The rest is cancelled with the 4 and one of the 3 factorials. And then there's another 3 factorial, which nicely works out to 6. So the answer is 5. Okay. Now that's if we were doing an intro to combinatorics class, we'd dwell more on this and how to compute it, but we don't actually care. All I want is an upper bound for the number of different trees. And this one's far easier to prove. One example, one way to prove that there's no more than 2 to the 2n trees of that shape, binary trees, is by giving an encoding for the trees using 2n bits. If that's possible and I can uniquely reconstruct the trees, then there can't be more trees than 2 to the 2n. And one way to do that is, for example, to say I'm going to write for every node in a depth-first traversal, has it got a left child? Yes, no. Does it have a right child? Yes, no. So that's one option. There's many others that are similar or slightly more useful for some purposes, but this is good enough. I guess I should say a pre-order traversal that we have. A clearly defined visiting order of the vertices. That clearly uses 2 bits per vertex, and if 2 trees differ, they have to differ at some point in the child links. What's less obvious maybe is that you can reconstruct the tree uniquely, but that's why it is important that you do a pre-order traversal, because then you can always keep track of which nodes still have open edge slots that we promised will be filled with children but haven't yet. And then because it's pre-order depth first search, you know which one is the next one. With that knowledge that if we have n numbers, there's only 2 to the 2n, a few less options for how the range max or range min queries can look like, we can come back to our previous approach of taking a big array and breaking it into small blocks, using sparse tables for the minima of the blocks, and then doing something else for queries within one block. That's the intra-block queries. We'll have to be a little more restrictive with the block size than previously. Before I just said big O of log n is sufficient. Now I need to fix the constant. If I put it, for example, at a quarter, then 2 to the 2b, the number of Cartesian trees, or the upper bound, is just square root n. So I've picked my blocks with this b so small that there's only square root n different ways how all the possible range min queries inside this block can look like, because there's only so many such binary trees. Which means there's going to be, among all those n divided log n blocks that we have of our array, there's going to be a lot of blocks that do the same. They have the same local answers. Of course, for different values and shifted in index, but if you locally look just at this block, they're identical. They're equivalent in terms of all range min queries. And so we can use exhaustive tabulation, which you guys already know from the alignment chapter. We're doing exhaustive tabulation on these small blocks. We write down the type and then do an exhaustive table of all the types and all their queries. So for every possible tiny little Cartesian tree, we're just pre-computing the stupid way all n squared or b squared range min query answers. That's going to be a bit wasteful, but because b is so small, we don't care. And then on top of that, we just write down for every block which type it has. Now, the extra trick why we can do this as a data structure is that we make sure these types are just numbers or bit strings. It's the same for a computer. So we can use them as an index in an array, as a kind of quick way, constant time way to jump to the right type. Okay. How to compute this in the pre-processing is also not hard. You can do any representation of a Cartesian tree using 2b bits. For example, the one I've shown you, it's as long as it's just a code, that's good enough. And then we also fill, going through all possible trees. Say we have our little tree like this. Now I would have to write this down in binary, but let's spare us the details, or might as well do it. Okay. This has no left but one right. This has one right, left but no right, and this has nothing. So that's going to be the same. And then I have 3 choose 2 different range min queries, not so many. I could ask between 0 and 1. That's these 2 nodes. Where's the minimum? Well, this guy is on top, so the answer will be 0. If I ask for 0 and 2, say, and the same block type, I also get 0. If I ask for 1 and 2, I get 2. Okay, so you can imagine we fill this for all possible trees of that small size and for all possible I and j, and we write down the answer. How much is this going to take us to do? The square root n block types, because b is so small, b squared combinations at most. So in still very, very little O of n time and space, we can fill this table. And with that, we found a solution for range min queries that, at least in theory, is perfect. There's nothing left really to say if you're looking at big O. It has linear time, pre-processing time, which you're going to have to look at the array at some point, and constant time for the queries, where we do this decomposition in inter-block and intra-block queries. And for the green ones, the intra-block queries, we use this table lookup. By the way, this is also how you solve longest common extensions in strings, where we used back then for tandem repeats, etc. There was this thing left open, right? Okay. So essentially best possible in terms of these times. It's a bit more complicated than maybe you want to implement. It turns out this exhaustive tabulation technique is really bad in practice, because to make it feasible to really have the space to write down this exhaustive table, you cannot afford big blocks. They're really tiny. Like it depends how much really you have to store, but maybe a dozen or so is already the limit. And then the rest is still this dividing by 12 or so in theory is log n, in practice is not such a big speed up. So oftentimes people choose slightly different implementations that have, in theory, a worse running time asymptotically, but tend to work better on current machines. But that aside, the theory problem's totally solved. And we can finally close this black box from last time.